Let us start with some general facts related to magnets. A freely suspended bar magnet oscillates for some time and then comes to rest along the magnetic meridian in the direction of geographic north and south. One end of the magnet points to the geographic north pole, called north-seeking pole or north pole of the magnet. And the other end points to the geographic south pole, called south-seeking pole or south pole of the magnet. This is because the Earth behaves as a huge bar magnet with its magnetic north pole located near the geographic south pole, and with its magnetic south pole located near the geographic north pole. We know that the like poles of two magnets repel each other, and the unlike poles attract each other. Thus, the north pole of the magnet is attracted by the Earth's magnetic south pole and vice versa. If a bar magnet is broken into two pieces, we get two similar magnets with a decrease in the magnitude of their properties. Thus, the magnets always exist in dipoles. Isolated magnetic monopoles do not exist. This implies that isolated magnetic north pole or south pole does not exist. Let us now discuss an activity about the magnetic field lines of a bar magnet. Consider a glass sheet with some iron filings sprinkled on it. Bring the bar magnet from the bottom of the glass sheet close to the sheet. As the magnet is brought close to the glass sheet, we observe that the iron filings on the sheet arrange themselves as shown. If we draw lines along the orientation of the iron filings, the lines will represent the magnetic field lines. Similar field lines are observed in the case of a current-carrying solenoid and an electric dipole. Let us now learn about the properties of magnetic field lines around a bar magnet. The field lines of a magnet start from the north pole and end at the south pole externally, which is outside the magnet. But internally, that is inside the magnetic field lines start from the south pole and end at the north pole. Thus, the magnetic field lines of a magnetic dipole are continuous closed loops. In the case of an electric dipole, the electric field lines start from the positive charge and end at the negative charge. Unlike magnetic field lines, the electric field lines are not closed loops. They are open curves. The field lines give us a visual impression of the magnetic field. If we draw a tangent to a magnetic field line at a given point, it represents the direction of a resultant magnetic field at that point. The magnetic field lines never intersect each other, because the resultant magnetic field at a point has only one direction. If we assume that two magnetic field lines intersect at a point, then the resultant magnetic field at that point would have two different directions, which is not possible. The magnitude of magnetic induction, which gives the strength of the magnetic field, is obtained by the number of field lines passing normally through a given area. If the number of field lines passing normally through a given area is large, then the field is considered to be strong. It is similar to strength of an electric field. If the number of field lines passing normally through the area is less, then the magnetic field is considered to be weak. An alternative method of plotting the field lines of a magnetic dipole is as follows. Take a bar magnet which is nothing but a magnetic dipole, and place it on a sheet of paper, which is placed on a horizontal surface. Then place a small magnetic compass at the north pole of the magnet. Plot a point on the paper indicating north of the compass needle. Shift the compass such that the south of the compass needle is observed at the plotted point. Then, again plot another point at the north of the compass needle, and then shift the compass as done earlier. Repeat the process to plot different points on the sheet around the magnet and note down the orientation of the compass at each position. We observe that the series of points plotted on the sheet are directed from the north pole of the magnet to its south pole. By connecting all the points, we get the magnetic field lines due to the magnetic dipole. The direction of the compass at different points on the field lines gives the direction of magnetic field at that point. Let us now learn the similarities between a bar magnet and a solenoid by comparing the magnetic induction of both. Finite number of continuous turns of a conducting wire wound in a helical shape represents a solenoid. We learnt earlier that the magnetic field lines of a bar magnet are similar to the field lines of a solenoid. Hence, a bar magnet can be assumed to be the same as a large number of current-carrying loops placed adjacent to each other. The two faces of the solenoid are similar to the poles of a bar magnet. The field lines leave one face of the solenoid into its exterior, and hence, this face of the solenoid is like the north pole of the bar magnet. The field lines enter the solenoid at the other face, and hence, this face is like the south pole of the bar magnet. Thus, the magnetic field lines of a solenoid are continuous closed loops similar to the field lines in the case of a bar magnet. We learnt earlier that if a bar magnet is cut into two pieces perpendicular to its length, two small bar magnets are formed. Similarly, if a solenoid is cut perpendicular to its length into two parts, two solenoids of smaller length are obtained. The two solenoids produce weak magnetic fields around them. Thus, each smaller solenoid acts like a small bar magnet. To make it more clear that the field due to a solenoid is similar to that of a bar magnet, we calculate the magnetic field induction B at a distant point on the axis of the solenoid and compare with the magnetic field induction at a point on the axial line of a bar magnet. Consider a solenoid of finite length with n turns per unit length. Let A be the radius, 2L be the length, and I be the current passing through the solenoid. Let the solenoid be placed such that the axis of the solenoid is along the x-axis of the coordinate system, and its center coincides with the origin. Then, the left end of the solenoid lies at the position -L, and its right end at +L. Let us consider a point P on the axis of the solenoid, and let R be the distance from the center of the solenoid to that point. To calculate the magnetic field induction B at the point P on the axial line of the solenoid, consider a small element of the solenoid of thickness dx, located at a distance of x from the center of the solenoid. Then the distance of the point P from the small element of the solenoid is r minus x. As n is the number of turns per unit length, the number of turns in the small element of the solenoid is equal to number of turns per unit length into length of the small element of the solenoid. that is equal to N into dx. We learned earlier that the magnetic induction B on the axis of a current-carrying circular loop at a distance x from the center of the loop is equal to mu naught Ia square by 2 into x square plus a square whole power 3 by 2. Thus, the magnetic induction due to the current passing through the small element of the solenoid at the point P on the axial line dB is equal to mu naught N dx Ia square by 2 into r minus x square plus a square whole power 3 by 2. The total magnetic induction due to the solenoid can be calculated by dividing the total length of the solenoid into number of small elements, and by integrating the magnetic inductions due to all the small elements, we get the total magnetic induction due to the solenoid. When we consider the small elements of the solenoid from one end to the other, the distance of the elements from the center of the solenoid varies from minus L to L. Thus, the total magnetic induction at the point P due to the solenoid is B is equal to integral minus L to L dB. That is equal to integral minus L to L. Mu naught N dx Ia square by 2 into r minus x square plus a square whole power 3 by 2. But Ian and mu naught are constant. Hence, the magnetic induction B is equal to mu naught Nia square by 2 into integral minus L to L dx by r minus x square plus a square whole power 3 by 2. When we consider the point on the axis of the solenoid at a large distance, r is much greater than a and r is much greater than x. Hence, we neglect the terms a and x in the denominator of the expression for B. Then, B is equal to mu naught Nia square by 2 into integral minus L to L dx by r cube. But the distance of the point P from the origin r is constant. Thus, B is equal to mu naught Nia square by 2r cube into integral minus L to L dx. On integrating and substituting the limits, we get the magnetic induction B is equal to mu naught Nia square by 2r cube into 2L. By multiplying the numerator and denominator of the expression with pi and rearranging the terms in the expression, we get the magnetic induction B is equal to mu naught by 2 pi into Ni2L pi a square by r cube. We learnt earlier that a current-carrying loop behaves like a magnetic dipole, and its dipole moment is given by M is equal to I into A, where A is the area vector of the loop. The solenoid consists of n number of loops per unit length. I is the current through the solenoid, and A is the radius of each loop. Thus, area A of each loop of the solenoid is pi into A square. The total number of loops in the solenoid is n into 2L, and hence the magnetic moment of the solenoid M is equal to N2LIA, which is equal to N2LI pi A square. Substituting M for the terms in the expression for magnetic induction B, we get the magnetic induction B is equal to mu naught by 2 pi into M by r cube. On multiplying the numerator and denominator with 2, we get the magnetic induction B is equal to mu naught by 4 pi into 2m by r cube. This is the same expression that is used to find the magnetic induction at a distant point from the center of a bar magnet on its axial line. Thus, a current-carrying solenoid and a bar magnet produce similar magnetic fields. Therefore, a solenoid is equivalent to a bar magnet and their magnetic moments are also equal. If the magnitude of the induction they produce at given distant points from their centers on their axial lines is equal,